Today I'm going to be presenting about some large-scale experimental tests that we conducted in Taiwan about 4 years ago, and we're finally just getting it out now. This is a collaboration that occurred between the Goya Institute of Technology, where I was at the time. Sociotech sponsored the work. INCRE and National Chung Kung University actually conducted the test. So without further ado, let's jump into it. So quick overview, I'll just talk very briefly about what is size effect, talk about the current ACI approach. I'll talk about the experimental program that we designed. The primary purpose here is just to broadcast that we have this data, and if you want it, we can share it. Specimen design, the test setup, and then the experimental results and the conclusions from the study. So size effect is a decrease in concrete unit shear strength with increasing effective depth. So it's an effect where instead of having the same for homogeneous material property that scales, well, it's the same across different depths, it actually changes as you go deeper. It was first observed in the 1970s by Connie, and it was recently codified in ACI 31819 related to the sub-S factor. This plot just shows the size effect factor here on the vertical axis versus the effective depth, dual units here. So the blue curve here shows the ACI 31819 approach, which is the square root of 2 over sum of 1 plus d over 250 millimeters, where d is effective depth in millimeters. And this effect implies that there would be a 36% reduction in unit shear strength when quadrupling from effective depth of 250 millimeters to 1 meter. And so that actually prompted our study. We said, well, is this actually true if we constrain other geometric parameters? So with that in mind, we set about this testing program. We tested small, medium, large size specimens. The small specimens had effective depths of 250 millimeters, medium were double that size, 500 millimeters, and then the largest ones had an effective depth of 1 meter. So these were all tripod specimens because we wanted them to be deterministic, makes it easier for our calculations. So we scaled the geometry. We kept maximum aggregate size constant, and the thinking there was, say you're going to cast a 4 meter deep foundation in New York, you're not going to scale your aggregate up to, say, boulders, right? You're going to keep a constant maximum aggregate size for workability purposes. We kept nominal compressive strength constant across the testing program also. We wanted to constrain that variable. With one exception, we got a little bit excited with the large specimens, and we wanted to test them with higher strength concrete. And then the control group was over-reinforced, and the purpose of that was to induce shear failure prior to electrical yielding. This is what the specimen reinforcement looked like. So I'll talk a little bit about some of the variables that we had here. So the diameters of bars, they were varied such that the ratio of bar diameter to effective depth was constant across the testing program. So for the small specimens, they were 9.5 millimeters. And for the larger specimens, they were 4 times that size at 38 millimeters. Those are the approximate number sizes if you're using imperial units. And all of them were high strength reinforcement. Again, we really wanted to make sure to induce a shear failure prior to electrical yielding. So they were 100 KSI bars. And I apologize for mixing units here. I've been working with dual units for a little while now. So at the ends, we had the anchorage plates. The purpose of that was to make sure that we could actually develop these high strength bars. There were 2 types of specimens, and I apologize, I have a little bit of a typo down here on the bottom one. That should be 0.5%. So in one type of specimen, we had 3 rows of 5 bars per span for a ratio of about 1.5%. And the other type, we had 1 row of 5 bars for about 0.5%. Again, effective depth, we varied that from 250 millimeters up to a meter. And then for concrete compressive strength, the typical compressive strength was 40 megapascals. That's about 5,800 psi. But in one specimen, we did go to 60 megapascals just to see what the impact of that was. And then aggregate size was kept constant at 10 millimeters for these. That was partly due to workability. For the small specimens, they were horrible. We had to make sure that we were going to be able to get the aggregate in between the bars. We didn't want to have any honeycombing issues. So again, small, medium, large is a familiar slide. So at the small scale, we tested 4 specimens. S1 was the smallest one. We tested 1 layer of reinforcement. S3A, 3B, 3C, those are repetitions of specimens with 3 layers of reinforcement each. At the medium scale, we repeated the same thing. N1, and then N3A, B, and C. And at the largest scale, we tested L1, L3A, L3B, and L3H. H is the one that had the higher strength concrete mix in it. This is an image showing the smallest reinforcement specimens. So these are S1, S3A, B, and C. All 3 of them fit on a pallet, so it gives you a good sense of the scale of the S-size specimens. These are the largest specimens, and these are two of the collaborators, which I wish could have been here today. So you can see just how large the difference is. In the background here, we've got the S specimens, and in the foreground here, we have the large specimens. So really, really a huge range of geometric variation here. Instrumentation and setup. So for sensors, we had displacement gauges, strain gauges, and cameras. Displacement gauges, we had some that were measured relative to the loading platen on the bottom side, but we are also very cognizant there would be some seating losses in the spherical variant that we use to support the specimens. So we actually had a frame that hung underneath it, and I'll show you that here in a couple slides. Strain gauges, we instrumented the longitudinal reinforcement at the bottom. There was no shear reinforcement in this case. And then we had lots of cameras all over the place so that we could see what the crack patterns looked like as we developed the test. We obviously didn't want to get close to this thing while we were testing it and mark cracks. This is just a quick overview of what the strain gauges look like. So again, we made a point to instrument different bars along the area here. I'm not going to show the comparisons of strain estimates versus results, but I will say they were quite good, and there will be more of that in the paper that's going to be coming out later this year. Loading, so there was an upper loading platen, and it was reacted by 3 lower loading platens. The upper loading platen was either 200, 400, or 800 millimeters in diameter, and the 3 lower platens were each 1/3 the area, such that the varying stresses would be the same with the upper and lower. And we loaded these monotonically to failure. Afterwards, we wanted to know more about what it looked like inside the specimens, like whether the crack patterns on the outside reflected the crack patterns on the inside. So we actually saw cut these things in half and looked at those crack patterns also and used that for some analysis. These were all tested at National Cheng University at an Increte facility in Tainan, Taiwan. It's a brand new, amazing state-of-the-art facility. It's a little bit hard to see here, but what you have here is the smallest specimen and then a human for scale over here. So way overkill for the smallest specimens. Here's again a view of the small specimen loaded in here with the upper and lower platens. We also used acetol down here at the base to make sure that they wouldn't be constrained laterally, which contributed to the vertical capability. This is a view showing some extra transducers that we had. So we had transducers on the bottom to measure displacement, but we also wanted to know how much they were sort of leaning inward. So we tested it, and so we also had additional transducers along the outside here. And then you can see the hanging truss down here, such that we could subtract out those seating losses. This is a complicated chart. I apologize for throwing it all at you at once. So what we have here is a comparison between the largest specimen and the smallest specimen. And so on the left axis, I'm plotting here the applied load for the largest specimen. On the right axis is for the smallest specimen. So the idea here is that the load should scale with the area. And so the area of the smallest specimen was 16 times smaller than the area of the largest specimen. So what I've done here is I've gone from 32,000 kilonewtons to 2,000 kilonewtons. But again, because they're 4 times smaller, 4 times displacement means that the displacement plotted here on the x-axis is going to be 4 times. So that's where that factor of 4 comes in here. And so one observation here that's immediately obvious is that the largest specimen did not reach, relatively speaking, the same strength as the smallest specimen. So that does imply a size crack factor for two-way shear for these specimens. Another observation here is they crack at approximately similar time, but that the post-cracking stiffness of the largest specimen is actually smaller than the post-cracking stiffness of the smaller specimen, sort of a tension stiffening result there. So that was an interesting observation there. In the single-layered specimens, it was really a similar story. So obviously, they reached lower strength than the triple-layered specimens, but we saw a similar phenomenon, cracking at approximately similar time, lower peak strength, and then also different post-cracking stiffness for the largest specimen versus the smallest specimen. I'm not going to get into detail about this, but this is sort of the result from our saw cutting assessment, which I thought was relatively interesting. We actually ended up doing projected views in SketchUp on these to try to understand what the sort of 3-dimensional crack patterns look like in these specimens. And what we observed in general was a sort of initial punching of that top platen, followed by a sinking and relative deformation of these two zones here. So just an example of one of the observations that we had from the tests. In terms of strength, I alluded to it earlier in those previous plots with the S versus the L. This is all 12 specimens plotted on the same plot. And so, again, we did see a strength reduction. So, here on the vertical axis, I've got a normalized error strength, and then here I have effective depth. About 50 megapascals on average for the small specimen, down to about 42 megapascals for the largest specimen. So about a 15 to 20% reduction in the strength, whereas ACI 31819 would have implied a 36% reduction. So the observation there is that there may be a floor on the size effect for two-way shear. Obviously, additional studies are needed, but it was an interesting outcome when holding all the other variables constant. So just to quickly summarize, we tested footings with effective depths ranging from about 250 millimeters up to a meter. That's 10 to 40 inches. We controlled geometries such that key ratios that have been observed to be important in the past were held constant. So that's say the bar diameter to the effective depth, the bar diameter to the concrete cover. The variables here were the effective depth, obviously. Constant aggregate size. So aggregate size was constant, but the ratio of bar diameter, aggregate size to effective depth was varied. The reinforcement ratio was also varied from 0.5% to 1.5%. The compressive strength was varied, but only for one test, so that was not really conclusive. It was just sort of an interesting observation. And what we observed was that there is a reduction in unit shear strength, but it's not as severe as would be predicted by ACI. So it was on the order of about 15 to 20% versus what ACI would expect, which is 36%. So that's it for me. Thank you all for your attention.
Really nice presentation. Very interesting stuff. I was just curious. I mean, obviously the ACI versions were intended for slender elements. Do you think if you had something that reduced the axial load or some larger bending moment relative to the shear, you'd still only see 20%? I'm surprised you saw any actually. I thought it would be zero for direct strut action type specimens.
Yeah.
So do you think that played a role in that difference between what ACI is proposing for slender beams versus what we're getting here in struts?
So something with a different A over E ratio?
Yeah, let's say. Yeah.
So that's going to be in part two.
No, perfect.
But yeah, so in part two we'll talk a little bit about
use your thunder then.
Yeah.
Thank you.
Yeah. Yes.
Did you model this one before the testing using a nonlinear model?
No. This was all purely based on hand calculations prior to the experiments.
Suppose if you do the modeling, what do you expect to see compared to the test result? Say you use for example, SAM or something to model the whole thing to try to figure out what the 3D effect could be.
It's a great question, and I wish I had a great answer for you. I don't really know what I would expect as far as the 3D FEA model of it coming on the linear model.
Nonlinear probably answers.
Yeah. Yeah, I don't have a great answer for you there. Great.
Or you try the strut time model.
Yeah, we did do strut and tie. So when I said hand calculations, we did do strut and tie calculations. I don't show it here, but we actually did do comparisons of the strut and tie estimations with also the measured strength at different steps. Those comparisons were very, very close to what we actually ended up observing.
Yeah, just a quick question. I mean, what's your explanation to the size effect? What's the underlying mechanism that different sizes exhibit different strength? What's your intake from it?
Yeah, so that's a very, very heavy question indeed. So I think far more intelligent people like Majant could definitely speak more to it than me. The way I see it is it has to do with the aggregate interlock. So again, speaking back to my Boulder example, I'm thinking of 3/4 aggregate in a 18-inch deep beam is quite different from 3/4 aggregate in a 20-foot deep beam. So I think it has to do probably with the ratio of the effective depth to the aggregate size and the interlock there. But that's a fractional mechanics problem, I think.
So did you observe larger cracks for the larger specimen? Or?
Yeah, I don't have any crack back information here, but it is in our World Conference paper, and again, available upon request if you wanted to see some of the cracks.